Yeah, this is kind of a tongue-in-cheek title. Actually, I had to get a little bit creative to stay under the title character limit because there's a lot of words in here. But essentially, one thing I've been really passionate about for probably the last, I want to say, 6 to 8 months has been in this like sort of space of cloud native. How do you run things sort of more efficiently, or as efficiently as you can? And there are just a lot of surprises, so I will go over those. So first of all, who am I? What do I do? So I'm Melanie at Airbnb. I'm a software engineer on our cloud optimization team. So in particular, my focus recently has been on the efficient use of cloud resources at our company. And so what is cloud efficiency? What is cloud optimization? And the best way I can explain it is that, traffic to your website or to your services, traffic goes up and it also goes down. And I actually think it's really interesting this year that traffic was probably the most anomalous for a lot of websites than it's been since anyone can remember. So really interesting year for traffic. And then the question is, your use of cloud, does it go up and down with traffic? And the answer might surprise you. Sometimes it does, sometimes it doesn't. And that's kind of the point of cloud efficiency, is essentially that when resources are dynamic, that it scales up and down with use when possible. And then otherwise, if you have static resources, what's the best possible use of those static resources at minimum cost? So when we talk about cloud resources, there's a lot of different sub-disciplines, like compute and storage. But for this particular talk, I really want to focus on compute and autoscaling and when it kind of goes wrong and how to make it work. So autoscaling, the thing that scales with traffic, right? I'm going to talk about Kubernetes autoscaling in particular, but I'll try to keep these lessons basically general purpose, so other kinds of resources, and I'll talk about other kinds of autoscaling in a bit as well. But let's take a look at Kubernetes autoscaling. So for those of you who are familiar with Kubernetes, you have a bunch of pods for your service deployed with a deployment and scaled with HBA or horizontal pod autoscaler. This is what Kubernetes autoscaling looks like for one service. And this is the YAML for that. So you have kind, HBA, a spec with minReplicas and maxReplicas, and you also specify a target CPU utilization percentage. So in this case, we are targeting 50%. So one question developers ask me is, what should I set minReplicas to? And this is actually an interesting question. In most examples online, you'll see 1 as the min, but for us, there's a few considerations that would make you want to have it be more than 1. So for example, if you want to have balance across different availability zones, if you want to be able to sort of survive an availability zone going down, or even an entire region going down, or even just degradation in one of these zones or regions, having your service balanced across those different zones or regions. So if you're in 3 regions, then maybe a minimum of 3 pods. There's another consideration, which is resilience against a bad pod. So if for whatever reason, one pod gets into a kind of weird state, if you obviously only have 1 pod, all of your traffic is going to something that's in a bad state. So boof, this pod disappears. And in our best case scenario with 3 pods, we have a 33% traffic drop while this pod is being replaced by Kubernetes. And in the worst case scenario, Kubernetes does not detect that there's anything wrong with this pod, even though there is. And so we actually have a 33% error rate or 30% high latency while this pod continues to run. So that might not also be acceptable. So try number 2. How many minReplicas can you sort of tolerate? So one thing I ran into in practice was, because of how often HPA polls to scale up your service, it is possible that for certain traffic spikes, it cannot scale high enough, fast enough to either handle the initial load for your service or just certain kinds of traffic spikes. So we had some services that had to set a relatively high minReplicas, much higher than 3. And this helps some services provide a buffer against these pods in an unexpected error or high latency states. And it just helps them if they have really, really pronounced traffic spikes. And then there's a similar question. So we're talking about the bounds of HPA, min replicas and max replicas. So with max replicas, what do you set that to? So HPA may not be able to scale high enough, fast enough for initial load, but we need to set max replicas similarly to prevent infinite scaling. So if we don't set it and we have this like sort of runaway pod, you can definitely sort of destroy your entire cluster if you don't put some limits in place. So what should you set max replicas to? It should definitely be something higher than you'd expect your service to ever scale to, but you don't want your service to, in the progress of an expected scale up, get cut off prematurely because it hit max replicas. So here's a more typical HPA for us, where we set min replicas to some number that's sufficient for this service, and we set max replicas to some number. So this is kind of a more realistic setting. And one thing that we noticed after doing this for several months was that curve replicas, which is my sort of metric for the current number of replicas or current number of pods for a service, is bounded between min and max. I mean, that's sort of the setting you made. So this is sort of like in the course of however much traffic it receives over time, it can't scale down further than 20 for this service, and it can't scale up further than 100. And one thing that's been really interesting is as traffic patterns drastically change beyond what was expected, curve replicas can get stuck at the minimum, and it can get stuck at the maximum. And I've definitely seen both happen in production. And so that was a little unsettling because I would talk to service owners and I would say, hey, you're stuck at max replicas, or you're stuck at min replicas, and they're like, and they would respond being like, well, I am targeting 50% CPU utilization, and I would say, actually, you're at 20% because you're pinned at one of these numbers. And so there was this disconnect happening where even though people were aware of what they were setting for their min and max, in practice, they sort of lost sight of that. Most developers remembered what they were targeting, and they kind of just assumed that their utilization was around the target. So what I found is that what developers expected was that, so we give recommendations for the minimum and the maximum CPU utilization. So obviously services shouldn't run too hot, and if you run them really cold, it's kind of a waste of resources. So developers set target, and they kind of expect the target CPU utilization to be bounded by this min and max recommended CPU. And the reality is that, sorry, my Zoom thing was like getting in the way. Okay, so the reality is that the actual CPU utilization can be much greater than the target CPU utilization if you set max replicas too low, because even though you need to scale the service further, it hit max replicas, so it's not going to be scaled any further. And so your target, your actual CPU can be much higher than your target. And similarly, your actual CPU utilization can be much lower than your target if min replicas is set quite high. And so we have, again, people who think they're around 50, but they're actually maybe at like 20 or even 10 or 5. And so the reality is quite different than what people expect. And basically what we found is that developers set min replicas and max replicas based on expectations of what their traffic would be, and those expectations can change over time. So the takeaway for me was that just because you're autoscaling your workloads in your configuration, you need to do an extra step to make sure they actually autoscale up and down effectively. So one thing I introduced was basically some stats-D metrics around HPA effectiveness for different services. And so I would actually report metrics if they're stuck at min replicas, if they're stuck at max replicas, what is their actual CPU utilization. And we actually wrote some alerts so we can alert service owners if their service is doing something unexpected. Okay, so that's Kubernetes autoscaling. But one thing that I think a lot of people forget about is even if they're using horizontal pod autoscaling for their Kubernetes services, what about the clusters that they're running on? And so people look at this picture, but they forget to sort of zoom out at the larger picture. So just because we're running these services efficiently and having them scale up and down, how do we actually handle the nodes on the cluster? What if the nodes on the cluster are too much or not enough? If the entire cluster is over-provisioned or under-provisioned? So in our case, we have clusters that are hundreds of nodes that are running also like hundreds or thousands of namespaces. And these pods are scheduled onto these nodes like this. So how do we scale the nodes? And I think in order to talk about cluster autoscaling, what you kind of really need to first think about is cluster scheduling in the first place. So to really demonstrate this, let's take a cluster. Let's assume it has 100 nodes because it makes the math easier. Let's assume that without any autoscaling, we have the nodes that are 75% full. And for my definition of fullness, I'm using request over capacity. So let's assume that work is perfectly balanced across nodes, which it is not usually perfectly balanced across nodes, but this is a more easier case to kind of reason about. So in this case, each node full, 75% full. And then we have a pod that needs 26%. The pod asks, hey, where can I go? This pod doesn't fit anywhere because all the nodes only have 25% free space, so it's off by 1%. And even though the cluster has, in excess 25% per node of capacity, the cluster actually cannot schedule schedule the pod at all. And so on average, you have to maintain X% free capacity to be able to schedule pods that use X% of a node's resources. In this case, we needed to maintain 26% free capacity in order to schedule this pod that uses 26%. So this kind of scheduling failure is really common, even in a cluster that is running at 60 to 70% utilization. So when you're talking about efficiency of compute and clusters that are running at, even in the most optimistic case, 60% usage, that's a lot of waste that's happening. So for us, this really limits us to our max cluster utilization. So we really wanted to run this more efficiently, essentially. So not cool. There's another thing I want to talk about, which is bin packing. So let's assume a different cluster setup where the nodes have a different request over capacity, and we use cookie cutter sized workloads. So in this case, we have a node with 74% and the pod is at 26%. And the kube scheduler says, you can fit on one of our nodes. So this has actually come up quite a lot, which is by default, Kubernetes allows you to request any amount of, like, let's take CPU, for example. You can request CPU requests in millicores, which can result in all kinds of different requests being made. So if you don't have any different cookie cutter size workloads, if every workload can be a special snowflake, scheduling and efficient bin packing of workloads onto clusters gets really hard. So one thing we've talked about is actually kind of constraining these. You can kind of think of like t-shirt sizing, like small, medium, large, but for workloads. And then you can actually reason about how to pack these onto nodes. But yeah, bin packing, very hard problem, obviously. So we're kind of getting into difficult territory. But in this case, there are ways for us to, by conforming the pods, the workloads to different sizes, to be able to schedule them in other cases where we would not have been able to schedule them. So that's a really neat idea. And then with autoscaling, we assume every pod is at 75% capacity, and we can actually, let's see, let me figure out how to explain this. So that's bin packing, and bin packing doesn't require autoscaling. But even with the most efficient bin packing, you can definitely imagine a case where you want to run the cluster tighter, and you just can't seem to schedule the pod because it just doesn't work out. Because the more tightly you run the cluster, the more likely you're to have essentially this collision where there's technically excess capacity on every node, but the pod doesn't fit. So where autoscaling comes in is what we do is that when there is a scheduling failure, the cluster can actually launch a new node and then schedule the pod onto that new node. And so we can actually run the clusters much tighter this way because we don't need to have manual intervention, manually scale up the cluster if there's scheduling failures. We can actually, as part of handling pod scaling up also scale up the cluster. So we can run things a lot tighter. And the pod says thanks. Oh yeah, and this is the new node. So it gets scheduled on. So cluster scheduling with autoscaling. So this is the same graphic as before with the Kubernetes pod and the deployment, but you'll notice it's a little bit different. This is the cluster autoscaler, not the HPA, and it's dealing with n nodes, not n pods. So conceptually, it's actually a fairly similar concept. And then of course, on every one of these nodes, we are running HPAs and running these different pods. So the question is, how do you actually implement something like this? So for us, you're able to use Kubernetes/autoscaler, the cluster autoscaler project, which supports this, but we kind of have to bridge the gap for how we implement this with our cloud vendor. So for us, we use AWS, and in AWS, you have EC2 instances, and the way that you autoscale EC2 instances in Amazon is with ASGs, or autoscaling groups. So we need to sort of bridge the gap between this cloud vendor abstraction and this Kubernetes concept. So we want to autoscale instances running in the cloud, which happen to be Kubernetes nodes. So one thing that's useful here with this concept of autoscaling groups, whatever cloud vendor you use, is that it can be used for all kinds of clusters. So we don't just use autoscaling groups for Kubernetes, although it's definitely useful there. You can imagine other areas where you have frequent changes in workload size. For example, CI clusters, developer machine clusters, things like that. And you can actually run lots of compute more frequently this way. Even in a world where you don't use Kubernetes, you could have a collection of instances for your service and you're just running them kind of on the bare VMs. You could also autoscale that up and down as well. So autoscale your clusters and make sure they schedule workloads effectively. You're not going to get any cloud efficiency wins if you don't actually schedule the underlying, if you don't autoscale the underlying clusters. Okay, so I'm going to switch topics a little bit to K8's fleet tuning. And the reason I call this fleet tuning is you need to zoom into a different level onto the pod, which actually has all these containers, and you need to really think about the overhead of these containers. So for us, each pod has a main container. You can think of this as the main web app or the cron job or whatever that's running your main logic. But in order to really have everything fit together nicely, we actually have many sidecar containers or side processes. And sidecar containers are things like logging, any service mesh type logic, stats metrics, any of these kinds of things are sidecar containers. And each sidecar container requests and uses resources. And therefore, so they request CPU, memory, things like that. So therefore, for every pod you have, it runs all these sidecar containers, and they add up to what we call a sidecar resource footprint. And this number can be quite large, and it's unexpected for service owners because they really only see their main container. So when you think about the overall fleet size for your service, you basically have two ways of scaling it. You can have fewer, fatter pods or many tiny pods. And it's not really clear on the face of it which is better, because you can configure them either way and still use the overall same amount of resources. And you know, it's not immediately obvious to many service owners I've talked to which is better. So, you know, which choice do you think reduces sidecar overhead? So fewer, fatter pods reduce overall sidecar overhead. Try saying that 5 times fast. Overall sidecar overhead. So for every pod, you know, you can think of this as sort of a tax per pod. So if you have fewer pods, you just have less sidecar overhead. And then how do we actually do that in practice? So essentially for your main container, you can request any number of CPUs. And so you can for example, you can request 3 cores or 6 cores. And in the case of 3 cores, if you're using HPA and you're targeting 50%, you would need twice as many pods to achieve that utilization than if you requested 6 cores per pod. And so it's a little bit confusing because it's actually the interaction of the CPU requests and how HPA scales your pods up and down given that. So fewer fatter pods means higher QPS is sent per pod to achieve the overall same utilization. And this arrow is traffic going to your service balanced across all the pods. One caveat that I want to mention, or a trade-off, one thing we noticed is that this can surface bottlenecks in your application code or even shared service framework or traffic layer code, shared libraries, and more. Essentially, if you have twice as much or 10 times as much traffic going through code that's never been verified to handle that much traffic, that's a major difference. And so one thing you have to do really is stress test any code path, any critical code path that it can really handle these sort of massive changes in traffic. And so we did have a few cases where we wanted to run fewer fatter pods, and we had to make some adjustments to shared libraries and code to be able to handle that increase in traffic. But overall, we were quite happy with the decision because we were able to run this traffic more efficiently through this shared application code, and we're also able to reduce our overall sidecar overhead in the fleet. So accounting for side process overhead and reducing the size of your fleet is actually quite significant. And what's nice about this is it's not just Kubernetes and sidecars. Any model where you have all these side processes that are running and taking up resources. So even if you're using something like Runit or Daemons or whatever, by adjusting it in one place, wherever you write that code, and then deploying it to all of your servers, you get that sort of reduction in waste all at once for one change. So this is in comparison to tuning one application where you have to, if you want to tune all of your applications to improve your efficiency everywhere, that's a much more heavy-handed kind of change than adjusting a shared resource and then deploying that one thing everywhere. So this is a kind of easy win. We found lots of easy wins where our sidecars were requesting too much or they were just doing things that were inefficient. That's really helpful. So on the topic of shared sidecars, clients, and libraries, there's a lot you can do here too. So if we go back to our Arcades pod, we talked about the sidecar containers, and kind of on this theme of tune once, use everywhere, each pod has sidecar overhead. So if you reduce the request of a sidecar based on actual usage, or you reduce the initialization time of each sidecar, you would basically tune it in one place and use everywhere. So one example is we had a container that handled logging, and it was requesting some amount of CPU that the original author of this sidecar felt was reasonable. But over time, the actual usage of that sidecar was much lower than what they were requesting. So they were essentially telling the Kubernetes scheduler to reserve much more space than the sidecar was using, and therefore much more space than the pod was using. So that was a case where the requests of the sidecar were not tuned based on actual usage. Another case is we have a sidecar that helps handle language translations, and there were some inefficiencies on how it started up and it downloaded translations. So the initialization time of this sidecar was quite long. And because our main container waits for the sidecar to start, the overall process, the overall startup of the entire sort of system of the pod was a lot less efficient. And so that was a place where by making improvements there, we sort of improved the efficiency of anything that used that sidecar, any of the services that used it. And one other idea that became significant for us was reducing the total number of sidecars. So instead of just optimizing each sidecar individually, taking a large look at like what's going on here, what are all these sidecars doing? Can we consolidate some of this logic that's really similar? So, hey, let's work together in the same process in my container. We're kind of doing the same thing. And now we can get rid of the other one. There's another pattern that I noticed, which is where we introduce a new sidecar container to replace the other sidecar container. The intention is to replace it, but maybe we forget to actually kill the old sidecar once we create the new one. So finishing migrations is actually, you know, a common thing that doesn't happen. People forget to actually replace something. And you know, there's some other things you can do for very involved migrations. For example, we're migrating from an HA proxy container to an Envoy container for service discovery. In this case, it's not that we've forgotten to delete the old HA proxy containers. They're still being used for some endpoints, and it's a little bit difficult to completely phase it out until we're 100% migrated to Envoy. But as we change edges from using HA proxy to Envoy, what's happening is that more CPU is being used in the Envoy container and less CPU is being used by the HA proxy container because it's doing less work. And so we can actually change the resource requests as the migration progresses to run things a little bit more efficiently. So we actually have done, I made several changes to sort of over time reduce what the old container was requesting without replacing it. And then as the new container comes online, it requests more. And this sort of just keeps things running efficiently during the migration. And the reason why we did this is because the amount these containers was containing was extremely significant. And so it's actually a little counterintuitive. Like on the surface of this, I thought it might be a bit of a premature optimization, but the numbers were really significant, and so it was worth doing. And when we talk about the K8s pod and sidecars, that's one thing, but another thing that a lot of people forget about is that the main container runs an application, but the application runs a lot of shared libraries and frameworks. So all of our applications use logic, shared clients and libraries that handle experimentation, site variables, internationalization, sync and async requests, DB clients, other service clients, I mean, metrics and logging clients. The list is really quite long. And the reason why I give all these examples is I think it's really worth calling out every case where you have shared code that is used by hundreds or, you know, however many production services. So a lot of traffic is going through these shared libraries. And by the way, if you don't have these as shared libraries, you might want to, because otherwise you're re-implementing the logic in a lot of places. So once you have the shared clients, libraries, and frameworks, you can actually optimize them. And then when you deploy the new version, services can talk to that. And it's sort of similar to sidecars in that you sort of tune once and use everywhere. So I'm a lazy person. I really like tuning something once and then getting wins across the entire fleet. It's really satisfying. So yes, tune once, use everywhere. And I'm going to call it out again, make sure they can handle the increased QPS. So there's a few changes we had to make to really handle these large changes in traffic, effective caching, being able to handle high concurrency using async when, you know, using async. In some cases, we were not using async. You know, things like thread safety. I noticed a few bottlenecks, some weird locking behavior in some shared libraries that didn't make sense. And so kind of cleaning up a lot of this code and running it super efficiently really helped us overall run a more efficient fleet. Cool, so efficient use of shared compute resources results in wins across the entire fleet. Okay, so that was all of the tune once, use everywhere type logic I used. But I'm going to talk about when it makes sense to tune applications, because I think this gets a lot of attention and it is worth doing sometimes. So let's zoom in one more time. Our main container runs an application. And so this is outside of the shared logic. This is the code, the bread and butter of what this application does. So we have a lot of applications, and I do think basic tuning is worth doing for a lot of applications. But when it comes to cloud efficiency, some applications are worth a lot more than others. So we actually prioritize the applications that have a large resource footprint or a high call volume. Those were really worth going over with a fine-tooth comb. So, you know, services that are in the critical call path when someone hits Airbnb.com, those are the services that really matter, not just for, you know, saving money, but for being really performant and responding quickly to user requests. So it's sort of like a win-win to tune these applications. And So basically these changes benefit not just efficiency, but performance and reliability. And I want to call out one misconception that I received a lot from some of our developers, which is that things around cost savings or running things more efficiently, a lot of people sort of pin that against like performance, reliability, availability. So people see it as this sort of like zero-sum game where like, you know, making this change is really dangerous, and like we're running things more tightly, and that could really result in serious availability problems. And I do believe there are cases where that's true, but a lot of the kinds of changes I talk about really are, you know, basic hygiene, running things the right way, and you also happen to run things more efficiently as a result. So I personally try to advocate for things that I think are relatively safe, or to do them in a way that is safe. And then it benefits all of these metrics. Okay, so here's some conversations I had with different service developers. So one, don't forget to profile your service. So I talked to a service owner and I said, hey, profile a service. And they said, well, I'm pretty sure my service is really efficient. I don't think I should do it. And then I ran a profile for them and I said, this profile shows that 30% of your CPU time is used to build this instance every single time you get a request. We have a factory for that. Why don't you use that? And so people kind of don't realize sometimes that there's these inefficiencies that get introduced over time with code changes that can make your service much less efficient. I mean, 30% of your CPU time is a lot. And so profiling, things like service flame graphs, seeing like the life of a request and where it's spending time, is really helpful. And this also can demonstrate any inconsistency, any problems or slowdowns also in shared logic, because a flame graph will show you everything, the application code, the shared library code. So you really get a picture on what's slow and when it is slow for different applications. Don't forget to handle concurrency. So I've had service developers come to me and saying, I use hundreds of threads, you know, is this a good idea or not? How do I work on this? And you know, what we kind of distilled it down to was a lot of these threads were blocking, and that caused performance issues at high volume. So, you know, breaking things down into using async when possible helped a lot of service developers. And of course, don't forget to check for leaks. So we had some people who ran their CPU checks, their profiles, everything looked pretty good, but it looked like their container was using more and more memory over time. Let's fix that memory leak. That's going to be inefficient as well. And one thing about memory leaks or memory usage patterns is you don't want to run things too tight. So in Kubernetes, I recommend people request more memory or be able to handle more memory than whatever they, you know, allocate to the JVM and things like that, because you really don't want to experience OOMs. So I think some people just, at least some developers I talked to, didn't understand that, you know, when you hit your memory limit, you get killed by Kubernetes, and that is a very catastrophic situation to be in. So one thing I do recommend is to not run things too tight in terms of the limits for your CPU and memory. You want to make sure that you're actually never close to really hitting what you'd expect your max, your peak traffic to be. So that's that on memory. So one other thing, everything is fine for my service until another service hits me with a bunch of traffic and I get totally overloaded. And this kind of can look like a finger pointing game where it's like, well, it's not really my fault. It's this other person's fault. It's not even the user. It's this other service that's calling me, or this collection of services that are calling me. And I cannot handle that. I cannot scale up fast enough for that. And we actually had to implement a lot of shared logic for basically what we call circuit breaking, which is explicitly handling these events where you're being really, your service is being pressured and overloaded. There's a few different strategies here, things like max retries, exponential backoff, configuring soft and hard dependencies. So if you're unable to talk to a service, you can still show something without like crashing and erroring. And so when you're in an overloaded state, you can sort of fail gracefully and show something without kind of just crashing catastrophically. And so here we used a shared framework. We've also started working on a sort of language agnostic solution with a service mesh that can really kind of handle a lot of this logic for you at the traffic layer. And so there is some sort of infrastructure building that needs to happen to handle this. It is actually quite hard for service developers to build this, correctly with all of their service-to-service interactions. Okay, beware of bottlenecks. I suppose I've mentioned this a few times, but I think it's worth repeating. My application is scaling fine, but I'm using a shared library and it is not. What should I do? So understand the known limits of shared resources. So sometimes it is true that the library says, hey, we can't handle more than this. This is what we're designed to do. And so sometimes, developers are misusing how they're calling a shared library, but other times we have found bottlenecks in shared clients, and it's worth collaborating together on fixing those. This is a new use case. This is a new a usage we need to support. Let's make it work. And this could kind of use its own whole talk, but language-specific bottlenecks actually come up quite a lot. So when we talk about cloud native and Kubernetes, a lot of this is at a lower layer, and it's language agnostic. But the truth is, there's a lot of really interesting interactions between basically how Kubernetes is implemented with C groups and how it handles sort of container resource management and what, like, for example, what the JVM requires. So for those of you who've ever sort of set JVM args, you'll probably notice that you either set XMS, XMX, it's hard for me to say all these, or like different min-ram percentage, those kinds of flags. I'm calling them out. There's a bunch of different JVM flags. The point is, it's quite hard to get these specific numbers or percentages to play along with Kubernetes and how Kubernetes requests does requests and limits for resources. And that's kind of a whole bag of worms. One thing I'll just mention is that how Kubernetes CPU throttles services that are spiking in CPU can lead to really long pauses. And if the service isn't garbage collection tuned properly, those long pauses can actually cause the service to not be able to garbage collect quickly enough, causing it to use more and more memory and then get killed. So that was a very interesting one where a CPU spike can actually lead, through these series of interaction to an kill. So I'm happy to talk more about that war story after this talk. But there was a lot of interesting stuff with JVM. And then we also noticed some interesting scaling limitations with Ruby services, or even Python, anything using Nginx as sort of the front load balancer or something like that. Its use of sockets can actually cause the requests on each socket can sort of queue up, and the queue can fall behind, and you can experience latency. Because we scale on CPU with our HPA, and we don't scale on like socket queue length or anything like that, there are a few service developers who found that it was a little counterintuitive that from a CPU and memory perspective, they were scaling fine, but from this other perspective, they weren't scaling fine. And so, one other thing to just call out is that it's not just CPU and memory. There's things like file descriptors or how you handle request queuing logic and things like that. So there's other bottlenecks that are either language specific or framework specific, or even just other kinds of primitives like disk IO. That can cause issues too, where you're just running out of space. So this is a whole other topic that I love, but we only have one slide, so moving on. There's another question I got asked a lot, which is how should I adjust my K8's resource requests? And I talked about this a little bit in the K8's autoscaling slide, but for K8's main containers, setting larger CPU requests, when you use the HPA, it'll reduce the overall size of your fleet and reduce sidecar overhead. And so we say, chunkier pods or fatter pods. So setting larger CPU requests actually can sort of tune your entire fleet size. So that's kind of a mind blower for a lot of people. Okay, and what about memory? Reduce memory if you're over provisioned, but not too much. We do not want and so when it comes to limits, setting limits in Kubernetes do have some overhead. One mistake I saw was people who set their memory limits based on, you know, let's say like a 24-hour window or a 4-hour window. You can't just choose any window and tune based on that. Our recommendation is to look at your past week and find the peak during that whole time. So during this large window, find the peak traffic and therefore the peak amount of memory and CPU use and tune based on that. You want to be able to handle your peak, not your average, especially when it comes to limits, which are used to sort of keep containers in check. Okay, so the takeaway here is to tune services which receive a high volume of traffic and or have a large resource footprint. It's generally the case that you may have a lot of services that don't do that much. Maybe they're in development, maybe they're test services, maybe they're sort of internal services. Those are not going to be as effective as tuning the services that receive your most critical traffic. These are the services that really would benefit from running more efficiently, and you'd also get the most efficiency wins out of tuning them. One more piece, efficient services-oriented architecture. So a lot of people like to talk about microservices, and I mean, we're talking about Kubernetes and orchestrators, so orchestrating services is sort of top of mind. At Airbnb, we're pretty careful, or we try to be careful, that we don't necessarily call them microservices internally, we call them just services. And the reason for that is when traffic goes up and down, you know, services receive traffic from users, but they also receive traffic from other services. The more services you have and the more services are interacting with each other, the more opportunities there are to just be inefficiencies in your overall architecture. So I'm quite hesitant to recommend that you should have, you know, thousands and thousands of production services interacting with each other, because that's a lot of opportunities for pretty crazy service call patterns to occur within that architecture. So, you know, one common interaction I had with some service owners was, hey, I said, hey, can you run more efficiently? You know, you're one of our top whatever most expensive services or most inefficient services. And they said, well, don't look at me. I just call these services, and these services just call me. I'm really a middleman service. There's not much I can optimize here. We'd have to optimize these guys, or sorry, these other services. And you know, when I hear "don't look at me," I just call these services. Well, that sounds like a code spell. There's basically an inefficiency going on. When you have these middleman services that just aren't doing very much, what you're actually surfacing is complex dependencies, hidden business logic. We've seen duplicate implementations. And so there's like this sort of inefficiency going on in your architecture at that point. And that's not cool when we talk about cloud efficiency. So one design principle we came up with sometime in the last year or two was we really needed an architecture solution for this problem. And the term we came up with was service blocks. So essentially what we want to guarantee is a clear separation of responsibilities between services, encapsulating logic and data, and having one directional dependencies. And if you want to, basically the outcome of this is less services and less dependencies. So we want to keep our architecture in check. It can kind of run away from you, and it is okay to say, hey, there's redundant services, there's unclear responsibilities, let's consolidate these and get one really great service out of it. And so we actually are working on some of the parts of our architecture that are quite inefficient. There's a lot of logic going on between service calls. Duplicating that service logic, or taking the duplicated service logic and arranging it into what we call a service block, which is really an abstraction. Then all the other services only interact with the block, not the individual services, and then we're actually able to simplify within that service block. So this is a really good way to, you know, when some designs kind of evolved into interesting beasts over time, to kind of take control of that complexity and simplify it and kind of keep the whole thing under control. So really important, simplifying your architecture reducing what I call service call fan out. So the amount of services you call and the amount of services those services call, that's the fan out. Reducing that overhead actually has tremendous implications for running your entire architecture more efficiently. So we're working on that right now, and that's really exciting to me too. Okay, so that was a lot of content. I have so much more I'd love to talk about when it comes to cloud efficiency. This was just compute. This was just Kubernetes and pods and containers and fleets. But these are sort of the takeaways: is to autoscale your workloads effectively, autoscale your clusters effectively, account for side process overhead, account for the overall size of your fleet of each service, efficient use of shared compute resources. Remember, sort of tune once, use everywhere. Love it, love easy wins. And then do, individual application tuning, in a sort of strategic way. Services with a high volume of traffic or large footprint. And then really the architecture piece, I think, is missing a lot. It's slightly less, it's not Kubernetes, but I think when you talk about cloud native, there's this really compelling architecture piece of how do you run a cloud native architecture as well. And I think that's worth calling out. So you can contact me at Melanie Cebula on Twitter. Happy to talk more about cloud efficiency. And yep, that's it.